Okay, so we've been talking on Monday, we talked about looking at distribution of means of samples, right? So let's just review it real quick. There we go. Okay. These lights usually aren't on, like these lights. Okay. Anyway, so our population. This review. This population was 5 heights of basketball players in inches. So we could form samples of size 2, right? So we got 10 samples of size 2. Each one of those samples has its own mean. So sample mean then can be thought of as a variable, and we can do our distribution of sample means. We can get a mean of the sample means and a standard deviation of the sample means. And then we could pick so this is you pick a sample size of 1, meaning basically you're just looking at the population. That's the first one. This is now samples of size 2. This is each one of these is a mean of a sample of size 2. And then each one of these is a mean of a sample of size 3. And what happens? The bigger your sample, the more likely it is the mean of that sample will be closer to the mean of the actual population. Should make sense. That's an important principle. That the bigger your sample gets, the more unlikely it is that mean will be away from the mean of the population, and a lot more likely it will be close to. So that's what we're seeing here. The bigger your sample gets, the more tightly those means adhere to the mean of the population, right? So that means with a larger sample size, the standard deviation is doing what? With a larger sample size, standard deviation is? She said going down. Agree with that? Yeah, it's going down. So standard deviation goes down with larger sample size. Okay. Here's a sample of size 5. Right? A sample of size 5 is everything. So the mean is going to be the only mean you're going to have of that sample is going to be the mean of the population. Okay, so this is how we calculate the standard distribution of sample means. This formula follows that principle. With a bigger sample size, you're going to divide by a bigger number. The square root of n is going to increase as n increases, and so then you're going to divide by a bigger and bigger number, which means your standard deviation of means is going to be less. It's going to decrease. All right, sampling error. So if you take a sample and take the mean, it probably will not be the mean of the population. It'll be some estimate of it, and we'll talk about that today, but it won't be so that the distance away from the actual population mean, and this is a magnitude thing here, so absolute value. So the distance that your sample mean is away from the population mean is called the error, sampling error, and that's important. And so that distance would just be, so if your population mean was 100 and you took a sample and you got a mean of 104, then the error was 4, right? The error was 4. And if you took another sample and you got a mean of 93, then your error was 7. Your error was 7. Your sampling error. Okay, so again, this is showing that with larger samples. So this is the actual population distribution. This is samples of size 4. That's the distribution of means of samples of size 4. This is the distribution of means of samples of size 16. So that's, see that principle again here visually, right? With larger sample size, you get a smaller standard deviation. Okay, and so then we talked about, and so the point of that was that if your population is normally distributed, then what about the distribution of sample means with a small sample size? So even a small sample size like 4, that's going to be normally distributed as long as the original population is normally distributed. So if you have a normal distribution, it doesn't matter how big your sample size is. It's going to be very small. Those sample means will be normally distributed. Okay? But if you have a skewed distribution or a non-normal distribution, we talked about what happens with that, right? So looking at the middle one, so just look at the middle column. This is clearly skewed to the right. Our median would be to the left, and the mean would be pulled up, skewed right. All right, so here is the sampling distribution for means of 2, or a sample size of 2. So we see that that is also skewed to the right. But then as your sample size gets bigger, like this case is down to a sample size of 10, it starts working its way, starts forming normal distribution. And so then kind of 30 is the magic number. No matter what the shape of your distribution is to start with, once you get up to large samples, like around 30 or more, then the distribution of sample means will be normal, regardless of what the population distribution is. Okay? And that's the central limit theorem. Central limit theorem says that for a relatively large sample size, and the number is around 30, the variable sample mean is approximately normal, regardless of the distribution under consideration, regardless of what it starts off looking like, the population. So here's an example of that. So here's this right skewed data, number of people per household. And these were samples of 30. They took 1,000 samples of 30 household sizes, and then took the distribution of those means. Clearly is normal, right? Clearly is normal. So this is from the population to sample size 30. And so this is how the central limit theorem works. Okay, so here is just kind of the overview. Of course, the mean of sample means equals the population mean, first of all. So that would be if you take every single sample of size of the same size, you would get the same thing. So if you just take one or couple samples, then your mean is not going to be the population mean, but a predictor of it, right? So because we know there's sampling error, right? There's sampling error. But if you took every single sample of a particular size from a population, then this would be true. The mean of the sample means would be the mean of the population. All right, the standard deviation of sample means will be the standard deviation of the population divided by the square root of the sample size. Okay, and here's these last two. If the population is normally distributed, so is the sampling distribution, regardless of how big samples you take. If the sample size is large, then the sampling distribution is normally distributed regardless of the initial distribution. Okay, so that's a good summary right there of everything. I think we did this one. So that's a little, I'm going to change this here. So let's do one, and then I'm going to put you to work. All right, well, so we'll do this one together. Okay, so it says that loan amounts. According to this study, the loan amounts of loans originated by a large insurance company lender have a mean of 6.74 million and a standard deviation of 15.37 million. Those are really big loans, right? A loan of, so the mean was 6.74 million and a standard deviation of 15.37. So just looking at those numbers, just think about this. Is that a normal distribution? Is that normally distributed?
Yes.
She said yes. No. You say no. Why not?
Standard deviation is like double the size.
Yeah, go ahead.
Well, if you take one standard deviation below
Uh-huh.
6.74,
Yeah.
you can have negative money and you can't have negative.
Right. You can't have it. We didn't have a negative loan. So if here is our 6.74, if we tried to do our plus or minus 1, so plus 1 would be, all right, 21 something, 21, 2201 or something, all right? Or 2210, 2211, something like that. And then, but what about below? So here's 0. We get some negative number. So the first thing we conclude is this can't be normally distributed. But then how would this be possible? How would it be possible that we have a mean of 6.74 and a standard deviation of 5.37? What does that mean about the distribution? What does it mean about the distribution? Yeah, we've got all these huge loans way bigger than 6.74, right? So the data is spread out. It's concentrated around maybe 6.74, but then we have some really big loans, way that are really big, and so they're spreading out the data, and so this is definitely going to have a huge right skew, right? This will have a huge right skew. Okay, but now we're going to do samples of size 200. So what about the distribution of sample means? So we have a very skewed distribution here, way skewed right. But we're taking samples of size 200. So our distribution of means will be normal, right? Like 30 is kind of the magic number. As long as you get your samples up to size 30 or bigger, then that distribution of sample means will be normal. So, so maybe our distribution looks like this. And way more exaggerated than that. But then when we get up to samples of size 200, it's going to be normal or something like this, okay? All right, so it wants us to determine the sampling distribution. So sampling distribution means what's the mean and standard deviation, or mu x bar and sigma x bar for samples of size 200. So what about the mean of the sample means? Yeah, that's easy, right? So that's easy because we know that the mean of sample means is the same as the mean of the population. And then the standard deviation of sample means is going to be our 15.37. What? That's it. Divided by the square root of the sample size. Someone crank that out. As soon as you get it, tell me. 1.09. And that's also in millions. So now, 6.74 with a standard deviation of 1.09, that gives us room, right? And so that's definitely going to be normally distributed. And that's going to be a tall, skinny distribution, right? It's going to be real tall and skinny because all with samples of size 200, all those samples are going to have means really close. The sampling error of each sample will be low, right? It'll be close to, the mean will be close to 6.74, so we get a low standard deviation. Okay, so then C, I think we already talked about. Why can you still answer parts A and B when the distribution of loan amounts is not normal but rather right skewed? Okay, why? Because we have a huge sample size, right? 200 per sample. What's the probability that the sampling error made in estimating the population mean by a simple random sample of 200 loans will be at most 1 million? Okay, so what are we saying here? We're going to take one sample of size 200. What's the probability that the error that we get, the sampling error, the mean, so we're going to take a mean of that, and what's the probability that the sampling error will be no more than 1 million? Okay, so what was sampling error again? So if this is our distribution here, so maybe this is, this is 2 standard deviations right here. So there's 1 standard deviation away. And so this is our 6.74 plus 1.09 plus another 1.09 minus 1.09 minus another 1.09. Okay? So we're going to take one random sample, find its mean, and we want the sampling error to be at most 1 million. So what is the approach, or what are we going to be solving here? What are we going to be doing to answer that question?
Quick question.
Yeah.
You said we're going to be turning this in on Blackboard, right?
No. Just no. I got some other work for you to do. So how are we going to do this? What does this mean? That if we want to say this, the mean of our sample has an error of at most 1 million.
You would take your mean, your sample mean, and do +1 and then -1, and then you would find the z-score.
Yeah, that's it. So this is +1 standard deviation, that's 1.09. So a little bit less than that, right in here somewhere, would be $1 million above the mean. And then we want $1 million below. And so we need our mean to fall in that range. So what's the probability that the mean falls in that range? So let's make a guess first. What would you guess the probability to be? So our standard deviation is 1.09, and we are going to, we want the sampling error to be within 1 million. So can you guess? You should have an idea of what our final answer is going to be.
60%.
She said 60. What do you think? What about 20%? What about 72%? Why? So why 60? Something. Why are they guessing 60? Yeah, right. So we know the plus or minus 1 standard deviation will give us that about 68% of the data. So now we're coming in just a little bit. We're saying we want to do a little better than that. We want to do at most 1 million of error. It's going to be a smaller range. So yeah, maybe 60% or 65 or 55 or something like that. So let's do it. So how do we get that probability? We're going to do the z-score for, so z of, so rather than following the formula, aren't we really saying it's going to be, we just want to be 1 above over, what is our, did anyone calculate this? Anyone get this? Oh, the 1.09, right? So we want to be 1 million above and 1 million below. So do you see how? Because what is the numerator is our x bar minus mu. It's the error. So the numerator in the z-score is the sampling error. You see that? It's x bar minus mu. So we could add 1, and say 7.74, but we're going to come back and we're going to subtract it out anyway again. We're going to go 7.74 minus 6.74. So just recognize that your numerator in the z-score is the distance from the mean, and that is basically the error. But then if it's to the left, it'll be negative. Okay, it'll be negative. Do you see that? Does that make sense? Okay, anybody got it? What's the z-score for 1 divided by 1.09? 0.92, and then negative 0.92, and so then we get our areas, right? To the left of 0.92 is how much area? 0.8212. Let's start doing it blue here. So 0.8212. And then to the left of negative 0.92? 788. And what do? We're going to subtract, right? So we want all the area to the left of that minus all the area to the left of that. As soon as you get it, shout it out. 6, 4, 2, 4. Someone else get that? Hello, class. Anybody home? Did someone else got that? Okay, great. So the probability that you take one sample of size 200, the probability that's mean has an error within 1 million of, that sampling error of 1 million, probability would be 64%. 64% of the time, you'll get the mean of a sample size 200 will be within $1 million of the actual population mean. Or the sampling error will be less than 1. That's what we're saying. The probability that the sampling error is less than 1 million is 0.6424. Okay, questions? Does it make sense? Okay, so I'm going to have you work on, for about 15, 20 minutes, have you work on some more examples here. And this is what we'll do. So I've got these sheets. When you work on these sheets, work this way. Don't work this way. Work like a mini sheet of paper, okay? And just put your name and the date in the upper right-hand corner. Just name and date. And show all your work on here. And then if you want to have any of this in your notes also, then do that, because you're going to hand these in. But then you could also put the examples in your notes. Keep handing up and down when they get out to the ends. I didn't count, but there should be enough. Everyone got one? Just leave them. Just leave them. Everyone got one? Okay. So, what's the day? The 25th? Yeah. So just name and date. Again, work this way. Work this way on the paper, not this way. Upper right-hand corner. Just name and date. Because we'll do this more often. We're going to do this more often. So like this might start replacing quizzes. So you work in class, you can work together. So if you want to work by yourself, you can, but you can work together, and you're going to get a grade on it. So I suggest that you work together. That's good. So let's do. I'll put up 2 at a time here. So let's try these 2 first. How about 7.76 and 7.78? Is it big enough to read in the back? Can you read that, Kuzmin? Selena, can you read that? Okay. Michael, you can read it? Okay. So let's do these 2 first, and we'll see how long this takes, and we might go on or do 1 or 2 more. So here we go. Oh, are you leaving too? All right. So chapter 8. Okay, so we're going to talk about what's called confidence intervals. So remember, inferential statistics. Inferential statistics means we take information from samples and we try to figure out what the population is like. So we've been dancing all around this, right? We've been putting all the building blocks in place. This is a huge part of statistics, is we've got some huge population, like all college students in the United States. And maybe it's, I don't know, numbers of hours of sleep that college students get per night, right? So average hours per night. We're not going to be able to get the whole population, right? So how would we figure out what the average hours per sleep that college students are getting per night? Well, we'd have to take samples. So from the samples, then we make conclusions about the population. That's inferential statistics, okay? And so that's a huge part of statistics. Okay, so a point estimate of a parameter is the value of a statistic used to estimate the parameter. Remember, statistics are values about samples. Statistics relate to samples. And parameters are about population. So this idea that we're going to take statistics and try to predict parameters, right? We're going to take statistics, things about samples, and try to predict parameters, meaning information about populations. That's inferential statistics, okay? So a point estimate of a parameter, or a point estimate of something about a population, is the value of a statistic, meaning coming from the sample, used to estimate the parameter. Okay, so mean is a perfect example. So I know this is small, but this is 36 new mobile homes. This is the prices of 36 new mobile homes. So it's a sample of size 36. Okay? And so a point estimate would be, let's take the mean of those 36 mobile homes, and then we'll say that's the mean of the population. We'll estimate that's the mean of the population. That's a point estimate. So we take the mean of the sample, and we say, well, this is the best we got, so that's our best guess at what the mean of the population is. Make sense? So here they're adding up all the prices of the new mobile homes. This is in thousands, I think. Yeah, in thousands. So $2,278,000 is the total price of all 36 mobile homes divided by the number of mobile homes. So I'll write that out again. 2278. That's the total thousands of dollars for all 36 mobile homes divided by 36 gives 63.28. So in other words, this statistic, this sample mean is $63,000, $63,280 on average for a mobile home. So we say, as a point estimate of the population of all mobile homes has a mean of $63,280. Okay? So that's the idea of a point estimate. Does it make sense? Using a statistic to say, this is what the value of the parameter is. Using this value from the sample to say, this is what the corresponding value of the population is. Point estimate. Okay? So here is litter size of some snakes. So a simple random sample of 44 female cottonmouths yielded the following data. Number of snakes in the litter. Okay, number of snakes in the litter. And so we want to use the data to obtain a point estimate for the mean number of young per litter of the population of all cottonmouths. All right, and the first thing they say is they gave us the sum of all these. All right, so they gave us a nice hint. So the sum of all of the values, that means what that's sum, and that's data value. So if you sum up all the data values, you get 334. And how many were there? N equals 44. So, can you find the point estimate for the population mean? The point estimate for the population mean. Well, it would just be the sample mean. So the sample mean would be our point estimate of mu. And how do you get the sample mean? Sum them all up, which they gave us that sum, divide by the number. Who's got it? What is it? 7.59? Snakes in the litter. So, we estimate the population mean to be 7.59 per litter. We got the sample of size 44. So, is that truly the population mean? No, because there might be sampling error, right? So this mean that we got of our sample may have some error from the actual population mean. So we just recognize that. But it's the best thing we've got. We don't know if the actual population mean is higher or lower than this. So the best we got is 7.59 for the population mean as a point estimate. Question on that? Okay, so here then this is the idea of confidence intervals. Okay, a confidence interval is an interval of numbers obtained from a point estimate. So we can make that point estimate, but then we could say, all right, the population mean falls in some maybe range that we're a certain amount confident about. So the interval is some interval around your point estimate, and the confidence level is how confident we are, in this case, that the population mean lies in that interval. Okay? And so the confidence interval estimate is basically these two things taken together. Your interval and how confident you are. So you take those two things together, and that's what's called the confidence interval estimate. Okay. Can I go on? So confidence interval is going to be, we're going to say plus or minus away from our point estimate, and then we're going to have a certain amount of confidence that the parameter that we're looking for is within that interval or not. Okay? That's the idea. Okay, so here's the prices of mobile homes. They're gonna assume that the population standard deviation is 7.2 thousand. So we're gonna assume that 7.2 thousand. Okay. Identify the distribution of the variable x bar, that is the sampling distribution, sampling mean for samples of size 36. Okay. So do we know what the population mean is? Have they given us the population mean here? Yes or no? No. We don't know what the population mean is. But they've given us what they believe the population standard deviation is. Okay? So then we're going to look at samples of size, what? 36. N equals 36. can we get a value for our standard deviation of the sampling distribution of samples of size 36? What would that be? That's right. It'd be 7.2 over the square root of 36, which would be 7.2 over 6. And is that 1.2? What about the mean of samples, mean of means of samples of size 36? Do we know what that is? No. So, but we know that it's equal to the population mean, right? We know that. So this is the best we can do. We have our standard deviation of samples of size 36, and we know that the mean of the means will be the mean of the population, which they didn't give us. Okay, but that doesn't stop us here. We can still make some progress. Identify the distribution of the variable x bar. That's what we just did. So there's the distribution. Mean of mu, standard deviation of 1.2. Okay, part B. Find a 95.44 confidence interval for mu. Okay, so what did we come up with before? We came up with an x bar before. It was sample size 36, right? Or no, was it 44? It was 44? Okay, so can't use that. All right, so what are we saying? We're saying a 95.44 confidence interval would be how many standard deviations above and below? 2. So we'd have mu plus 2 times 1.2 and mu minus 2 times 1.2, or mu plus 2.4 and mu minus 2.4. So that gives us what's called a confidence interval. So if we had a mean of a sample of size 36, we would add 2.4 to it, and we'd subtract 2.4 to it from it, and that we would be 95.44% confident that the actual population mean fell within that range. So actually, this is really x bar here. So we get a mean of a sample of size 36. If we add 2.4 to that, and we subtract 2.4 from that, then we'd be 95% sure that the population mean fell in that range. Okay, and then we'd be 5%. It'd be like a 5% chance that the population mean fell outside of that. So that's the idea of a confidence interval and confidence level. Okay, so here is 20 samples of 36 homes. 20 samples of 36 homes. And here's the means of all those. Okay? And so they did, for each one of those, they did the confidence interval. They added 2.4 above and 2.4 below. Is that right? Yep. So this is plus or minus $2.4 thousand to get those confidence intervals. And so then here's the point estimate, and then here's the confidence interval. So here are those sample means, and then here is the confidence interval, adding 2.4 thousand above, 2.4 thousand below. And you see you've got all these different confidence intervals for all these different point estimates. And they made an assumption. They assumed, okay, just let's assume that the population mean is 65. And when they took these 20 samples, they saw that for 19 of them, the population mean fell within the confidence interval, but then for one of those samples, the population mean fell outside the sample. So for 19 out of 20 samples, mu fell in the 95% confidence interval. Which is 95% of the time, the mean fell. So 19 out of 20 is 95%. See, 19 out of 20 is 95%. So 95% of the time, the actual population mean fell in the confidence interval of the point estimate. Okay, so let's try an example and we'll be done. So let's do... Okay, so here's, no, we just already did that. So let's look over here. Here we go. Let's do this one. All right, so we've got home improvements. This is the budgets of 45 randomly sampled home improvement jobs. Okay? In dollars. Okay, so home improvement, they took 45 randomly sampled home improvement jobs, and here was the amount that they spent on their home improvement job. Okay? So first let's get a point estimate. They told us that the sum of all those is 129,849. So if we summed up all the data, we get 129,849. How many data values are there? 45. So we're going to take 129,849. It's the sum of all those and divide by 45. And what's our point estimate? Nice and loud. 5.3? Thank you. Okay, so the average price of a home improvement job was $2885.53, and we can use that as a point estimate of all home improvement jobs. That, you know, throughout the whole United States, we could guess that the average was 2885, but we know there's sampling error. The true population mean is probably higher or lower than that. So we form a confidence interval. So we want a 95.44 confidence interval for the population mean of home improvement jobs. So we're going to use our point estimate and we're going to build an interval around it and say, okay, we're 95% sure that the actual population mean is within our interval. Okay, so we're going to assume that the population standard deviation is 1350. So we need the, what do we need? We need the sampling distribution standard deviation. So we're going to take 1350 and divide by square root of 45. As soon as you get that, tell me. 201.24. So that's for samples of size 45. The standard deviation is $201.24. And we got a sample mean of 2885.53. So how do we build our 95% confidence interval? We're going to go 2 of those above the mean and 2 of those below the mean. And then we can say we're 95% sure that the true population mean lies in that interval. So let's find that interval. So we're going to have our 2885 plus 2 times 201.24, plus or minus, Yeah, sure.
I got slightly different than 201.24. I got 0.25 instead of 0.24.
Okay, so that's not,
Doesn't matter.
yeah, that's 1 penny, right? So that's,
All right, I was just making sure.
yeah. If you're off by $10, then that's important, but off by 1 penny is just a rounding error. So let's get the two values here. What's the lower value? So if you take 2885.53 minus 2 times our standard deviation, anybody got that?
2483.05.
Nice and low?
2483.05.
2483.05 up to, go ahead.
3,288.01.
Do we have confirmation on those two numbers? Someone else got it? Good. Okay. So what did we just find out? We had this point estimate of the mean population of 2885.53, but there's inevitably error, right? So inevitably the actual population is not that. So if we find the distribution for samples of size 45, we can get our standard deviation for samples of size 45, and we can do 2 above and 2 below, and we know that 95% of the data falls within those two. And so we can say with 95% certainty, the true population mean, or the true average budget for all home improvement jobs is between those two values. So that's our 95% confidence interval. Okay, anybody have a question? So you've got the regular online homework, due Sunday night. And we made it. We covered everything in that. So you're good to go. Question?
Did you just want those two problems?
Yeah, just the 2 that we did before. You can stack those up here on your way out.
You said I could finish this in your office. Try to turn it in there or just keep it in.
Different amount.